Welcome to this presentation on spatial analysis and decision making. We're going to specifically discuss the following aspects. First, what is the difference between GIS mapping and analysis? Second, determining the various forms of measurements in a GIS. Third, explore proximity analysis. Fourth, explore topological or vector overlay analysis. Fifth, examine some specialized analysis such as geocoding and network analysis. And finally, discuss how GIS and data analysis is integrated in a decision-making workflow process. One of the earliest forms of analysis that made use of spatial data was the mapping of cholera deaths in London, England in 1854. Dr. John Snow plotted cholera deaths on a paper map using point locations for households where the deaths occurred. He then visually inspected the resulting map and observed a distinctive pattern. Many of the deaths were occurring around a particular pump. He inferred that the water from the pump could be a factor in the deaths. The pump was shut down, and soon after, the cholera deaths reduced as well. This is a good example of how one can use spatial data to explore spatial thinking and arrive at solutions to problems. GIS mapping is related to GIS analysis. In GIS mapping, the focus is usually on visual appearance and patterns. In GIS analysis, the focus goes one step further to quantify spatial relationships. The spatial relationships can be classified into the general categories of measurements, where we determine physical aspects such as patterns, distances, and so on. Proximal, where we determine what is near and what is far. Topological, where we determine connectedness and neighbors. Directional, where we determine compass directions, and this is closely related to the first category about measurements. We will explore all of these categories in more detail. The first type of spatial relationship is measurements. Measurements in the vector data model is based on the coordinates of the points, lines, and areas. You will also appreciate that measurements are only accurate if the spatial data is in some projected coordinate system, meaning the data refers to a flat surface of the Earth. Measurements can be anything from recoding to aspects such as pattern, distance, cost distance, and area or perimeter. Many of these measurements can be obtained directly or are stored as a column in the attribute table. For recoding, we are interested in reclassifying the data into different categories. For example, we might need to combine commercial and residential to create a new aggregate urban category, maybe to compare urban with agricultural. In the end, the attribute table now contains a new column where all commercial and residential elements are given the same code in the new column, say 1 for urban. For patterns, the intention is to statistically describe the geographic arrangement of objects on the surface of the Earth. In order to make this comparison, 3 standard statistical data distributions are used. These are random, as seen on the left, uniform, as seen in the middle, and clustered, as seen on the right. In the uniform arrangement, the data is distributed with no particular order to them. In the uniform arrangement, the data points are equally spaced from other points. In the clustered arrangement, some data points are grouped together. The real-world data is then compared with these statistical distributions to determine whether the real-world objects are random, uniform, or clustered. For distance and directions, simple geometry calculations are used. For example, if we know the coordinates of the starting point and the ending point of a line, then Pythagoras' theorem can be used to find the length of the line. This functionality is usually present as a button or menu item in the GIS software. Note that the data must be in a projected coordinate system for this measurement to make sense. Sometimes though, the measured distance is not a straight line. You might require to ascend or descend hilly areas to move from your origin to your destination. The actual distance you travel will be different from the straight line distance, and in addition, the effort or friction would be different. This distance traveled that takes into consideration friction or effort is called the cost distance. One example is traveling on the road network. Because of traffic conditions and stoplights, for example, The time to travel from one point to another is called a travel time, which takes into consideration the barriers on the road network. For measuring areas, a computation algorithm called the Simpson's rule is used to calculate the area. The algorithm performs calculations on each vertex that forms the polygon area to produce a final area value. The perimeter is simply a sum of the lengths of the lines that form the shape. A second type of spatial relationship is proximity analysis. In proximity analysis, the goal is to determine what is near and what is far. One example of proximity analysis is buffering. In buffering, a zone of influence is drawn around either the point, line, or polygon. The extent of the zone is determined by a distance that the user provides. That zone of influence can be used to either include or exclude objects that falls within it. In simple buffering, the zone of influence is the same distance away from the point, line, or polygon. However, in complex buffering, the zone of influence can vary. For example, primary roads can be buffered a larger distance than secondary roads to represent the fact that maybe noise levels might be greater on primary roads. The third type of spatial relationships is topological or vector overlay analysis. This type of analysis is not the same as transparency overlays, which is only visual. If we know which points fall in which polygons, and which lines intersect which polygons or lines, and which polygons are adjacent to which polygons, then we have the capability to ask spatial questions related to distance, containment, intersections, and adjacency. These simple analyses can be combined in complex ways to drive all the possible spatial analysis questions that a GIS can answer. We will look at the point and polygon spatial relationship as an example to give us an understanding of what exactly happens at the computer and database level. We have a data layer showing the nests of owls. The nests attribute table contains a unique identifier for each nest and a description called place. A second data layer shows the forest type. The forest type attribute table contains a unique identifier and a description called forest type. We now perform the overlay analysis using the owl's nest layer as our source data layer. That means the forest type data layer information will be added to the owl's data layer to show the forest type that each owl's nest is located in. Once we perform the spatial analysis as discussed previously, we can then query the database using SQL tools to extract information that we need. For example, we can write SQL statements that will allow us to extract all the owl's nests that are in deciduous forests. As we discussed earlier, the SQL statements are written by selecting visual elements from a graphic user interface, so no programming is required. Other specialized types of spatial analysis exist. Geocoding and network analysis are popular examples. In geocoding, a highly accurate street network file together with a regular street address is processed such that the street address is positioned accurately within the network. For example, the street address of patients who visit a clinic can be geocoded and positioned on a street network. Then questions such as how far patients travel to visit the hospital can be useful to determine aspects such as health services. In network analysis, again, a highly accurate street network file is used. One question that can be asked is how long will it take me to get from an origin to a destination? Usually, distance is minimized in the calculation on how to get from one point to another. A typical example of this is the regular bus routing services that may be available in your city. In this example, a source and a destination is selected together with time of the day, and the bus routing application provides output to show an entire routing plan for you to use when taking the bus on this particular network. This is a practical example of network analysis in operation. Given the spatial operations we have discussed previously, it should now become clear how the GIS is able to answer these spatial questions listed here. As mentioned earlier, these questions become increasingly sophisticated as you move from the identify type questions to the spatial modeling type questions. GIS analysis is usually part of a workflow that includes the spatial data, the data analysis, and then the interrogation and debate by decision makers, and finally the results, which is to improve an existing condition. More and more it is becoming clear that a GIS is more useful when it is tightly embedded in an institutional structure and there is a target problem that is being investigated.